Okay, today is April 8th, 2020, and we're going to continue our discussion of amines in this section of the notes. So the first topic we're going to look at today is the physical properties of amines. You're going to notice that they have similarities to alcohols, but they're not exactly the same. So we know that alcohols have high boiling points, and we attribute this to their polarity and the fact that hydrogen bonding is very important. Excuse me. So what we see here is a list: methane, methanamine, methanol, and ethane. And we see that the melting points vary somewhat, with the nitrogen compound and the alcohol both having much higher melting points than the alkane molecules. The boiling points, the changes are even more dramatic, with the alcohol coming in at 65 degrees and the methanamine coming in at minus 6.3. If we go down to the propane, ethanamine, and ethanol examples, again, we see a similar trend. So in this trend of things we see that amines have higher melting points and boiling points than we expect, or based on their comparison to alkanes, but if we start comparing them to the alcohols, we see that they're lower. What this tells us to some extent is that the nitrogen molecules do undergo hydrogen bonding, but for whatever reason, this hydrogen bonding is not as strong. So amines, much like alcohols, are capable of hydrogen bonding. However, their hydrogen bonds are not as strong, or maybe not so much not as strong, but is not as an important factor in their physical properties. The reasoning behind this is twofold. We have oxygen having two sets of lone pair electrons, so this means that oxygen can undergo two hydrogen bonds at any one time. And the second thing is that the electronegativity differences between oxygen and nitrogen is not as polar, so it doesn't require as much pull of electrons, and therefore the idea of stabilizing charge on the atom itself through hydrogen bonding is not as critical. At any rate, this is the effects that we observe for amines. Now let's look at the acidity, and basicity of amines. So one of the interesting things about amines is that they are an acid. They can also act as a base, and then that base can also act as an acid as well. So the idea here is that nitrogen compounds have a lot of functionality. They can act in a number of different ways. So amines can act as both acids and bases, and due to lesser electronegativity of nitrogen, they're not very acidic. So if we look at an amine versus an alcohol, alcohols have pKa's that are around 15. If we look at this and we deprotonate and we see a nitrogen with a negative charge, this is the nitrogen acting as an acid, and the pKa of these species are around 35. They're just not very acidic. Amines can also act as Bronsted bases. So shown here, we have some acid of some sort, and the lone pair electrons on the amine will pick up a proton. We form the conjugate base of our acid and the conjugate acid of our base, a nitrogen with a positive charge. Now, as I've already stated, the acidity of amines is not very strong, but the pKa is around 35. So this compares to around 16 for alcohols, obviously not very acidic. One of the weird things you're going to see here, and this is actually not a spelling mistake, if we have this NH2 group, this is an amine, and then we have this negative charge on nitrogen, and this is called an amide. Okay, the weird thing is we use the same name for two groups. If you have a C double bond O NH2, that is an amide, and then a nitrogen from an amine that has a negative charge is called an amide. We just pronounce the same word differently, and it has a different meaning in our world. But anyway, sorry for the confusion, but this is the way things are named. At any rate, a pKa of 35 is not an acidic species, and as a result, there are some high pKa's. We've already seen one example of this. One of the hammers with respect to very strong bases that we sometimes use is LDA, lithium diisopropylamide, which is shown here is a structure. This is one of the stronger bases, that we have used from time to time in the class. The basicity of amines, these are kind of cool too. You see here that you can protonate them fairly easily, Kb, to form the ammonium ion and hydroxide, and these are moderately strong bases. Okay, so let's look at some pKb data for these. Shown here is ammonia, methanamine, I guess N-methyl methanamine and NN-dimethylmethanamine in terms of naming these materials. The pKb's are 4.76 for ammonia, 3.38 for methanamine, 3.27 for N-methylmethanamine, and 4.21 for NN-dimethylmethanamine. Now, something that hopefully you remember from Gen Chem. If you don't, I'm reminding you right now. But we kind of do want you to remember this. Please remember that if you add the pKa's and the pKb's of the bases and the conjugate acids, what will happen is you should get 14 each time. So the pKa of the conjugate acid of ammonia or ammonium ion is 9.24, 10.62, N-methyl methanamine 10.73, and NN-dimethyl methanamine 9.79. So we have these two numbers. Now, this is really cool. But why is it cool? So why is this such a big deal, the acidity and basicity? If you think about these, all these pKa's and pKb's are accessible in water. So biologically, these are very, very convenient acids and bases that can be used in these particular cases. So what you'll find is that there is a lot of biological systems that employ these species as acids and bases in a variety of reactions. Okay, now the effects of substituents on pKb's. As you would expect, there is going to be an effect on the pKa if you add electron withdrawing or electron donating groups to these species. So if you add an aromatic ring to an amine, an aromatic ring is intrinsically an electron withdrawing group, and what we see is a drop off in the pKb. It goes to 9.37. So this is a weaker base, and that's to be expected. There's going to be a little less electron density on the nitrogen, and as a result, that less electron density is going to make this a little less basic, because in Bronsted base, it is the picking up of a proton. The nitrogen is going to be less willing, because it has a little bit less electron density, going to be less willing to pick up that proton. So electron withdrawing and donating groups are going to have the same types of effects as we've seen in carboxylic acids and alcohols and these sorts of things. Okay, so the net result of all of this is that an arylamine is much less basic than an alkylamine. Synthesis of amines, we've kind of already seen some of this. In other cases, we haven't. Alkylation is a very, very convenient way of making amines. So for example, if we react ammonia with an alkyl halide, we can displace in an SN2 type fashion the alkyl or the halide to form, I've changed the halide here, that's really sweet. But anyway, it should be Cl minus here. I apologize for the confusion, but we get the ammonium ion, which then chloride should pick the proton up off the nitrogen and form HCl. I don't know why I changed that, really bothering me now, but I'm not going to change the notes because I'm lazy. At any rate, the major problem with this reaction is that once the nitrogen has been alkylated, the propensity of this to alkylate again is very, very high. So the net result is that you tend to see multiple alkylations at the nitrogen. So why is this? If you think about it, alkyl substituents are inductively electron donating. This should make the nitrogen more electron rich and therefore more nucleophilic. So this is not a surprising result at all. We can actually justify it based on things we already know. So basically what I'm saying is that we have this now N-methyl or methanamine reacting with another equivalent of our alkyl halide, chloride again, and we get bromide again. It is amazing, folks. These sorts of notes don't just happen by accident. You have to be actively not trying to get this bad. But anyway, online this will be bromide, and I apologize, but it should be chloride in all of these cases. Sorry about that. Another method is indirect alkylation or indirect alkylation of a nitrogen species. So we've already seen that cyanide is a very good nucleophile. If we react this with an alkyl halide, we displace the halide. I got X right this time. So we form our nitrile, and if we reduce this, and we had two methods of doing this from last lecture, in fact, lithium aluminum hydride, or we could just hydrogenate, so H2 with some metal catalyst, and this will form the amine in this reaction. So on the next page, we have a fun example. It's a fun example because it has two alkyl halides. So if we treat this with sodium cyanide, we'll get a dinitration, the addition of two nitrile groups. I've turned the molecule because I was running out of space. At any rate, we then take this dinitrile compound and treat it with hydrogen gas and rainy nickel. That's going to be our catalyst, and we get our diamine compound. This is a relatively good method, although working with cyanide is a little bit dangerous. And you also get an increase in your carbon chain length, so you increase the complexity of your molecule. So this is a nice way of doing it as well. If you don't want that chain increase, what do? Well, you can use a reagent called azide. Azide here is the Lewis dot structure of that particular material. You can see it's got two negative charges and a plus charge. It's a linear molecule. It turns out that it is an excellent nucleophile. Remember that we talked about the toxicity of cyanide, and part of the toxicity of cyanide was because it's such a good nucleophile, or all of the toxicity of it, whatever. And azide is just as good a nucleophile. So again, what you do is you treat an alkyl halide with azide, and then once you form this azido compound, you can reduce it to the amine. This reaction occurs via SN2. Azide displaces the halide. I've shown no halide here, probably a good thing because I'd probably get it wrong. And then once the azide product is formed, you can reduce it. And usually the reducing agent that's used is lithium aluminum hydride, acid water workup, and you'll get your amine compound. This works fairly well, but of course the lithium aluminum hydride is a fairly aggressive reagent, so you can't use it with some of the material. Another way of putting a nitrogen on a compound is something called a Gabriel synthesis. And in the Gabriel synthesis, what you do is you take this 1,2-dicarboxylic acid, treat it with nitrogen, or ammonia, heat it at a paltry 300 degrees Celsius, and you'll get phthalamide. Now, phthalamide is an interesting molecule because the two carbonyl groups in here really increase the acidity of this NH group. It's very easy to pull off. It's got a pKa of about 8.3, and that means even a weak base can pull this off. But what you have is you now have a nitrogen with a negative charge, and it's not a very basic one. So in this case now it can start acting as a nucleophile. So once it's deprotonated, it can act as a nucleophile, and we can get some other types of reactivity out of this. So you can see we're near the end here, yay. We're going to take a weak base, potassium carbonate, and we're going to deprotonate this material to create the anion. Now this will act as a nucleophile, and it'll undergo an SN2 displacement of the bromide here. We're going to do the reaction in DMF to enhance nucleophilicity. Remember, DMF helps SN2 type reactions. Once this is displaced, we get this material here. And now we're going to hydrolyze these CN bonds with water and sulfuric acid. We get our dicarboxylic acid over here, and we form an ammonium ion, which we treat with base to form the amine. This is a nice method that avoids the polyalkylation reaction. Okay, you have a test on Friday. Good luck with that test, and I will be talking to you again next week. Have a great day, everyone.